these small deviation analysis, which is kind of typical. So what I'm thinking about is that I postpone the least square, which is not complicated anyway, but it's a least square. Okay, so all about that is, so what I'm just surfing around is I postpone, so we will discuss later. Okay, all that. I move to the Kramer-Rao bound so that we can make exercises. Okay? So that's my goal. So this means that I write here to do. Okay, all that. So I jump to another chapter only for exercising convenience. So go to, go to parallel at this point. Okay? And then we go back. We will go back into the least square later on. So just to prepare you for also for the intermediate test. Now, about the Kramer-Rao bound, the Kramer-Rao bound sets the lower bound for any unbiased estimator, which means, is the lower curve. You cannot go lower than that. Okay, so that's the Kramer-Rao bound. And so the way to derive the Kramer-Rao bound, I'm not proving, so I'm not giving the proof of the Kramer-Rao bound, because using itself is just, it's not complicated, but you find it complicated. And then, proof, deriving the proof will be a nightmare. So let me skip the proof and I give you the result. Okay? So the way to start is the following. Now, assume that I have an estimator. And the estimator is unbiased. It's important unbiased. Okay? Assume that I have an estimator. Estimator is unbiased. Which means that if the true parameter is theta 0, so the estimator has the estimated value equal to theta 0. This is saying unbiased. Then the Kramer-Rao bound sets the bound of the covariance of the estimate. Which means you need to consider that this vector is a set of parameters. It's amplitude, phase, frequency of sinusoid 1, amplitude, phase, frequency, sinusoid 2, amplitude, phase, frequency, sinusoid 3, whatever. Okay? Now, the covariance of that one, so the covariance of this estimated value, according to the estimator, whatever, is always larger or equal than the Kramer-Rao bound. Now, when I write in this way, means that the covariance minus these matrices are positive semi-definite, which means if I take this difference, so when I write a matrix A is larger or equal than matrix B, means that A minus B matrix, okay, is larger or equal 0. Means that the quadratic form, I don't know, let me call X, don't call X, let me call alpha, let's go A minus B, alpha is larger or equal 0. This is the implication, okay? So when I write a matrix is larger than another, it doesn't mean that the entry are larger. It means that the difference is positive definite or positive semi-definite. Semi-definite means that it is larger or equal. It's just a jargon, okay? It's okay if you say larger or equal for me. Even if technically you should say it's a positive semi-definite. Which means that if I make a quadratic form associated to this difference, the quadratic form is larger or equal than 0. Okay? This is the formal implication. Now, what does it mean in practice? In practice means that since on the covariance along the diagonal, I can find the variance. So let's just make it a refresh. The refresh of the following. When I write covariance of, it's better I write there because it's a reflection that is better that you have in front of you. Okay? Because sometimes you make a mistake on that. Okay. Now, when I write covariance of theta hat, depending on x, okay, this is a matrix. And this matrix contains the variance on theta 1, variance of theta 2, so it contains the variance on the diagonal, okay? And off diagonal, it contains the covariance between theta 1 hat and theta 2 hat. And I don't know, here for instance, the covariance of theta 1 hat and theta 3 hat, and so forth. Okay, just to remember. So that means that along the diagonal here, okay, I get the variance. So when I write that the covariance of theta hat x is larger or equal than the Kramer-Rao bound matrix, when I write this way, means that this matrix here, this is a matrix, okay? Okay? So this one is a P times P, and this is a P times P. It means that any term along the diagonal, so if I take a variance of theta hat x k, the variance is is the one that is in the position kk along the diagonal. Okay, this one is larger or equal than the Kramer-Rao bound matrix calculated in the position kk. This is the implication. No. So that means that beyond the semi-definite or so, but the most important property is that the variance, which is what you wanted to know, where can I read the variance? Okay, you read the variance along the diagonal of the Kramer-Rao bound matrix. No, life is not that easy. Now, how to get this magical matrix? Now, this magic matrix, called magic. Okay, so this matrix, so the Kramer-Rao bound matrix, is obtained by inverting another matrix. And this matrix is called the Fisher information matrix. So what I need to do is the following. So I need to, before writing the formula, so what I need to do is I need to set the problem, okay, and isolate the parameter theta, which is a p times 1, is a vector. Okay. Let me write the word isolate and order the parameter. Then step number 1. Step number 2 is create the so-called Fisher information matrix, in jargon called FIG. Now, this Fisher information matrix is related to the set of parameter theta. So which means that the Fisher information matrix is a matrix itself, and it is a P times P. Then, once I created this matrix, I will tell you in a second how to make it. Once I created this matrix, you calculate the Fisher information matrix to the -1. So, you need to first set the problem. Second, you need to fill, to create, to calculate, okay? Then you need to compute the inverse. Then, once you're here, the Kramer-Rao bound matrix is exactly that inverse. And that means that the covariance of any estimator is larger or equal, or with the definition that we said before, of this Kramer-Rao. So along the diagonal of the inverse of the Fisher information matrix, I get the variance that I'm looking for. But you know, since the entry along the diagonal is obtained by inversion of the matrix, you need first, unfortunately for you, you need first to compute all the entry in Fisher information matrix. And that's the bad news. But now, you know, after so many bad news, I give you the good news, a very good news. The very good news is the following. No matter the problem you're doing, no matter how complicated is that, no matter whatever you want, okay, the maximum likelihood, most of the cases, implicit or can be calculated numerically because I need to maximize something. Okay? But the Kramer-Rao bound or the Fisher information matrix can be calculated in closure form. So that's a good news. So which means the lower theoretical bound that in any estimator can be calculated in a closure form. It might take time. Some time to calculate the Kramer-Rao bound, it might take 1 week, 2 weeks. Okay? I took 1 month, you know, some time ago to calculate the Kramer-Rao bound. But that's, once I calculate the Kramer-Rao bound, then I started working on the estimator. So usually the professional works in the opposite way than you think. The professional, first they get the Kramer-Rao bound, the lower bound. Then they say, okay, I can now make better than this. Then I start working on the estimator. And you know, once I get close enough to the Kramer-Rao bound, I say, okay, I'm finished. You see? I don't work in the opposite way, which means first I started finding the solution. No, first I found the bound. And then I compare any estimator with the bound. And then when I find one that goes onto the bound, I'm happy. I don't do anything else. Most of the case, when I found an estimator that is in some way efficient means it's using the data best. Efficient means it goes into the Kramer-Rao bound. Then my next goal is to try to reduce on the computational effort. Because you know, you will learn in your professional life then when you start making, you know, an algorithm or an estimator or you know, or a solution to problems, and you try to propose that, then the answer is it's too complex to put into the computer. It's too complex to put into the processor. And so the next step is to start to erode a little bit on the computational effort, and that means that, you know, the more you erode and the more you depart from the Kramer-Rao bound. Okay? So it's, you know, it's this kind of job. So you start, you set the bound, okay? So it's like this way, you know, like you have seen during the numerical exercise that you have a signal to noise ratio defined, whatever, and then you have mean square error. You remember, you know, the exercise, you log, and you get this as a Kramer-Rao bound. And Matera told you this is a Cramer-Hall bound. You don't know how to calculate, but you know it's a Cramer-Hall bound. And then, I mean, once you calculate that, you cannot make it better than this. No question. You know, and this has a lot of implication because once you have the Cramer-Hall bound, you can start designing your system. Let me tell you why. Assume that, you know, I can tolerate this as a maximum value, which means, you know, the mean square error should not be larger than this. Okay, so that means that the signal to noise ratio should be larger than that. And if I get a suboptimal estimator, this means that it's more larger than that. Okay? So, you know, what I do is the following. I mean, I first set the bound, then I calculate, I can derive my estimator. I make some approximation, usually. Now, if I make my one approximation, my estimator goes this way, let me say, I'm happy. Okay? Because, you know, my system is working this region, so I mean, I'm already on the Cramer-Hall. I'm not following 0.1 dB, which means, you know, a negligible gain. And now what you do, you start tuning it. So you change one part of the estimator, and the curve goes down. No, too much. Then you try to change a little bit, and then the curve is perhaps is departing there. I don't care. In this area, it never works. You see? So this is the kind of job. So your life would not be to set an estimator. Your life would be to compare the estimator to that. And by the way, let me say another thing that, you know, is something that I routinely make, but I never say because it's so obvious for me, but you know, it's not. So I need to say, okay? So every time you come to discuss for the homework, then I mean, I say, don't stress the point during the lecture. The Cramer-Hall bound, you know, is also telling you what is the minimum performance that you can expect. Now, it is also useful to check if the estimator is correct or not. Because if you have an estimator which is going that way, you make a mistake. Which means, usually the problem is that you define as SNR the signal to noise ratio in one metric, and you implement the SNR in a different way. Which means the theory is mismatched with the implementation. Okay? So this is a typical way. So anyway, so this is how, let me say, the professional works. Okay? And they make a usage of the Cramer-Hall. So the value of this course is to define every time the bound. And this is the reason why, you know, I'm making these deviation about the course on evaluating the Cramer-Hall bound. Now, let's read it. Okay? So, so the covariance of any estimator is larger than the Cramer-Hall bound matrix. Remember, the Cramer-Hall matrix is the matrix which is P plus P, has the same size of the number of parameters, which is obtained by the inverse of this J matrix. And this J matrix is the Fisher information matrix. Okay, good news. Now, how to compute? Well, the way to compute it is by taking the log Lacuille function and computing the derivative of the log Lacuille with respect to the parameter theta I and theta j to calculate the entry, the element ij. So, and you know, which is equivalent. Now, these equivalents you can find in the book. So this is equivalent to calculate the first order derivative with respect to theta I of the log Lacuille, multiply the first order derivative of the log Lacuille with respect to theta j. Everything expectation computed on theta equal theta 0. Now, this means that the Cramer-Hall bound depends on the value. Depends on the parameter that I'm getting. Okay? I mean, that's it. So the difficulty is to compute this one. Now, once again, you know, I might take 1 day, I might take 10 minutes, I might take 10 days. Of course, you know, for exercising to you, I don't give you something that takes 10 days. But you know, I mean, 10 minutes, 15 minutes for 10 minutes for the written exam is typical, right? So now, yeah, perhaps takes time and patience, okay? So you know, it takes and it's quite delicate. One comment. In maximum likelihood estimation, okay, we use the log likelihood and make simplification on scaling coefficient. Okay, usually we say I have a scaling term, I neglect because you are maximizing something. Okay. In Cramer-Rao bound computation, you need to keep all. No simplification. You cannot say, oh, this is a common coefficient and I take it out. No way. Okay? So for this reason, sometimes, you know, the formula are not manageable. So you need to use Mathematica or Make or I don't know what kind of software we use. So I had to compute the Cramer-Rao bound this summer, and I use, I think, Mathematica. I don't know. I let the software to compute. It came out the hypergeometric function, you know, it was complicated, but that's it. I mean, it's called hypergeometric, but it doesn't matter. It's someone computed. Okay. So anyway, now this is what I told you. So the variance of each parameter. So the Cramer bound evaluates the bound of the covariance. And the variance is along the diagonal entry. Okay? After after Fisher information matrix computation. This sentence says exactly what I said. Now, in case of numerical simulation, as you know, Matera did, it is customary to evaluate the mean square error. So what you do, you evaluate the mean square error. And the mean square error, you remember that the mean square error is variance plus bias. The Cramer-Rao bound says this is 0. Okay? So if the bias is not 0, then you don't get the Cramer-Rao. So for instance, if my curve is like this, I don't know if my estimator here is affected by a bias. Perhaps you know it's simply a bias, but you need to check if it is a bias. So you need to look carefully. So for instance, you know, you simulate in a small data set, you check if it is affected by a bias, you evaluate the bias, you try to search what is generating this bias, because a bias and estimator means a distortion of the estimator, means that you know there is something that you can do better. Okay. Now, perhaps the bias is something that is already included in the way that you are designing your estimator. Perhaps you know that your estimator is biased, and then you try to do everything you can, provided that the estimator contains a little bit of bias. So, I don't have a right solution for any problem that we are discussing. I'm simply giving you a box, personally, with many tools, okay, to solve the problem when it's necessary. Okay? There's not a tool that makes everything, solve any problem. Now, before going on that, let me tell you how to compute it. Okay, so this is again to do. Now, this is a very nice and good news. And by the way, if you have an experiment where everything is Gaussian, and you can write that the observation, the data, is Gaussian in some way, where there is a mean and covariance that depends on the parameter. It might be the mean depending on the parameter and the covariance depending on the parameter, or only the mean but not the covariance. It depends on the case. Now, if we are in this setting, we are happy, because in this way we can calculate the Cramer-Hall bound in the closure form. So we have a formula. Now, if you go on the back of every written exam, you will see this formula. Okay? So there is no question to learn by memory this formula. Okay? Now, this formula is saying that the entry ij of the Fisher information matrix is computed by the partial derivative with respect to theta I of the mean, covariance inverse, and partial derivative of the gradient with respect to the mean with respect to theta j. And then for the covariance is a little bit more complicated. Okay. Now this one is in closure form. So it's what we need to use. And what is my goal is to use this one. Now, let's see, for instance, assume that my model is a model where I have a signal that depends on the parameter plus a vector of noise. And the noise is affected by a certain covariance. And now, for instance, in this problem, if you remember on the maximum likelihood, we said we need to write the quadratic form, and then we need to optimize the quadratic form numerically. Okay? And that's it. I stopped it there. And then I say, I can show you. And then I said, if this is the dual problem to solve. Here. This is on the estimator. So this is the estimator, and this is the Cramer-Hall. Okay? So for the estimator, what I need is, no, this one is the D. Yeah. Okay, so in this case, so the best I can say is that, to get the maximum likelihood, I need to minimize this one. That's it. It's a numerical procedure. And so I stopped myself. I cannot say anything on that. I can only say that in order to find the maximum likelihood, I need to optimize this function. Stop. Now, what about with the Cramer-Hall? Well, with the Cramer-Hall, I can compute for this, let me say generic, this is the most generic one, I can compute the Fisher information matrix. And then, it's a matter of computing it. And then for this Fisher information matrix, I can calculate what is the lower bound. So, once again, in this example, if comparing two maximum likelihood estimation, okay, that needs numerical optimization. Cramer-Hall bound can be computed in closure form. That's the good news. So that means that, I cannot find a way to make the estimator. But this line, I know where it is. I know the lower theoretical bound. I cannot get better than this, but I can calculate that. Having a lower theoretical bound is saving a lot of responsibility to you. Because, imagine that, you are having a bridge, and the bridge collapses. And they say, oh, you didn't use exactly the maximum, the best possible bet. I compare with the Cramer-Hall bound. I go as a Cramer-Hall bound, and I cannot do better than that. And this is releasing this for responsibility. Okay? So it's like there developers, they're a branch of engineering where, you know, they try to make everything according to the some standard specifications. And the standard specifications are also a way to release your responsibility, because you make everything according to that. Like the doctors. The doctors, they use protocols. Protocols is not like a telecom protocol. Protocol is just procedure, okay? And so when you go to the doctor and the doctor is using that procedure and you die and you say, someone says for you, okay, says, you know, and someone goes and say, oh, but you know, my parents died. I say, I'm using the protocol. The protocol means the procedure, you see? So the procedure is releasing a lot of responsibility, okay? So it's one of the pain of engineers, you know? It's one of the pain of every person that has a responsibility, okay? Because, you know, I mean, you don't get money for the work you do, you get the money for the responsibility you take. Okay? And so, you know, and at a certain level, okay? And so that is the closure form. Now, let's validate for something. So if I consider a linear model, then, you know, the Fisher information matrix is this one, okay, which is simply by computing. So I can need to calculate the derivative of h times theta. Since it's linear, I can calculate the derivative in closure form. Now, if I compute the Cramer bound, it's h transpose cw h to the -1. And now this one says that the Cramer bound is equivalent to the covariance of a blue estimator and the covariance of the maximum lateral. And this is covariance of numerical exercises of Monte Carlo test. Of Friday, last Friday. Okay? This is what, you know, you discussed in material. Remember, you have that one. Okay. Now, if you know, if the noise are correlated, I can calculate in the closure form as well. Now, let me take an example. Let me take an example now, and I want to use an example here. I want to make the first example on linear regression. We're making the example of linear regression. You know, you remember the linear regression is when I have a set of points and I'm calculating a linear fitting line. Okay? So this is A, B, and this is A. This is a linear regression problem. So we have seen time ago, we have seen that this can be modeled as 1, and then, you know, a vector representing all the time samples, multiplied by A0, B0, plus that. Okay. See some kind of. Now, you know, let's assume that W is normal with a 0 mean and covariance W. Now, first of all, I mean, I can use, this is linear, so this is H, this becomes theta. So this problem is linear. then I can use the maximum likelihood estimation. And the maximum likelihood depends, okay, it can be calculated, you know, in closure form. So theta 0, theta hat, the estimated value. I'm copying, huh? I'm not reinventing the wheel. It's H transpose H. We did it. H transpose X. Okay, so this is the estimator, and the estimator is linear. Then using this, we can calculate the covariance. Now, to make it simple and, you know, straightforward, let's make the case that CW is equal to sigma squared W multiplied by the ADSP. So that means all noise samples are uncorrelated. Okay, independent. Since it's Gaussian, so it's independent. Okay, so that means that, you know, you have these points which are fluctuating. Each of these points is fluctuating, you know, because of the Gaussian. Okay, so there is a noise affecting. Good. Now, you know, my goal is not to get the estimator, because the estimator is that I want to know how much do I gain if I increase the number of samples from n to n plus 1. So what the economists call the marginal gain, which means how much do I gain in variance, which means how much the variance is reducing if I buy one sample more. So if the number of samples that are here n, they go to n plus 1. Okay. Now, how to calculate that? So first of all, in order to calculate that, I need to calculate the Kramer-Rao bound. So let's calculate the Kramer-Rao bound for this case. So I give you the closure form here. So let's assume that, you know, let, as I said, CW equal to sigma square identity to make it easy. And let make that TK is equal to K times delta T. Samples are regular in time, which means regular sampling. Because the previous formula was for the regular amplifiers. Now, so, you know, I go to the Kramer-Rao bound, and then the Kramer-Rao bound say that covariance of A hat, B hat should be is larger or equal than the Fisher information matrix. What is the Fisher information matrix? You know, if I go back, so I go. It's this one, so it is H transpose CW to minus 1 H. So it is H transpose CW to minus 1 H. Everything to the minus 1. Now, I make a remark. So since this CW is sigma square identity, CW to the minus 1 is 1 over sigma squared. Okay, so this one is 1 over sigma squared W multiplied by the identity. But now, since this one is a scalar, this scalar goes out. And so, since it goes out, it is equal to the inverse of 1 over sigma squared. So it is sigma squared. So that one is equal to sigma squared W, and then it is H transpose H to the minus 1. Okay. Now, so I want to keep it, you know, in a formal way. So if I keep it in a formal way, where did I calculate it? Okay, so this one is is equal to the n is the number of samples I'm copying, okay, is the sum of k, k going from 1 to n, sum of k is going from 1 to n, and then sum of k squared. Everything to the minus 1. So, you know, this is one of the sum of the series that can be computed in the closed form. Okay? And then, you know, I have a 4 entry. I need to invert a matrix of 2 by 2. And so the outcome of this one is, I give you already, so it is 2 times 2n minus 1 divided by n plus 1. Then the off diagonal is minus 6 n plus 1, the same, and the b term is 12 n minus 1. So this is the Kramer outbound. Now, first, what can we say? We can say that, you know, from that, my conclusion, that's what I want to discuss. My conclusion is the following. The variance of A n is larger or equal than sigma squared w, then it is 2 times 2n minus 1 divided by n plus 1. And the variance of b is the slope, okay, is larger or equal than sigma squared w, and is 12 and n squared minus 1. Now, so that means really it's everything here. So, you know, I'm just copying. As I copy, you know, it's reading. So now what I can notice here is the following, that remember it is A is the slope, B is the slope, and A is the intercept. So the variance of B on the slope decreases with the cubic of the number of samples. So that means that the slope, the more I add the point, the better the slope is, the better I estimate the slope. Because it goes with the cubic of the number of samples. So for a very large number of samples, you know, very large, this is approximately 12 divided by n cubic. And the other is 4 times sigma squared w divided by n. Which means that, you know, I cannot get the very accurate intercept. Intercept is the coefficient A. If I have a small number of samples. On the other hand, my slope is better constrained because this is not cubic. Now, if I go from n to n plus 1, and you know n is very large, but well, you know, I drop, so I have my variance, which is dropping significantly. So, you know, if I make from n to n plus 1, so for the variance of A. Okay, and you know my dropping, so the ratio between what I was and what I get is simply, you know, it's n divided by n plus 1. So I mean the ratio, the gain is linear because the denominator, it depends linearly on n. So if I, you know, what I can calculate is the following. Okay? So this is the variance of A, okay, and that is 4 sigma squared divided by n, and here is 4 sigma squared divided by n plus 1. So you know, I mean, if n is very big, n plus 1, it doesn't change it that much. Okay? Consider n is 100. Okay? So if I go from 100 to 100 plus 1, you know, yeah, I go better, but you know, it's not that big. If I look at the variance of B, well, it is 12 sigma squared, and then it is n cubic. And in this case, it's 12 sigma squared, and it is n plus 1 cubic. Then you know it's the cube of the first, the cube of the second, and then it is 3 times for that. Okay, so you know approximately this one is 12 sigma squared. I mean, roughly, it is 3 times n cubed. But decreasing quickly. I gain a lot. Okay, so you know, I mean, what I get is that if I want to gain a lot by introducing an additional point, what I need to do is that I need to increase the number of points when I'm computing the coefficient B, and not much on the coefficient A. But there is a physical interpretation of that. The physical interpretation is the following. You know, imagine that I am this is 0, okay? And 0, and I'm holding this in 0. So you know, every point is vibrating. But you know, the vibration on the faraway point is affecting less the slope rather than the vibration on the early point. Okay? So because an early point vibration, you know, look at here, is vibrating a lot. But the vibration on the early point is less and less and less and less effective. Okay? On the other hand, you know, A. What's happening A? You know, A, no matter where I have the vibration point, I mean, it's always affecting the intercept. So this is some way natural if you think that, you know, you have a rigid line. Now, I can read something. Here, I have some numbers. This is minus 6n to n plus 1. What does it mean? It means that, you know, if one variable is changing in a positive way, the other is negative. Okay? Because they are anti-correlated. It's negative. Obvious, right? I don't need so many equations to say that if this one is going up, the other is going down. Okay? But you know, I mean, what I read is that these two parameters, A and B, they are correlated. So they, you know, they are linked to one another. So, you know, these two parameters, when there is these terms in the camera one is not zero, the two parameters are in some way related to one another. Okay? So the parameters, you know, they are in jargon called, they are coupled. The parameters are coupled. Coupled means that, you know, if I change something on one parameter, the other is changing as well. Okay? Now, but you know, any mechanics, and probably the mathematics said if they did the meccanica razionale, I don't know how many did the meccanica razionale. Nobody, right? They did it. Good. Okay, so and you know, if you do courses on mechanics, okay, you know that if you want to describe any rigid point, any rigid body, you describe the rigid body by two movements. One is the translation, A, and the other is the rotation. But you know, it would be very bad to describe translation in keeping in the corner and rotation, I mean, from the angle. A very convenient way would be to describe this stick, holding the stick in the center, the body center, and describe translation of the body center and rotation with respect to the body center. This one is a privileged system. So intuitively, I say, if I just describe in this way, so that means that, you know, I mean, what's happening in rotation is totally decoupled from what's happening in translation. I translate, I rotate. So what does it mean here? Well, it means that, you know, I need to rewrite a new system of axes, which is a new color. And this new system of axes, rather instead of putting the 0 here, it puts there. And so I value the samples as a positive and negative. It's just a matter of renaming the samples. Okay? Now, let's see if we can gain. So actually, the intercept that I'm computing is this one, A hat, in this pinky column. Okay? So let's remake the analysis. Now, if I remake the analysis, which, you know, I'm making a little bit thicker, okay? So if I remake the analysis, the Kramer-Rao bound is computed the same way. H is the same, except that now the sum is going from minus n(i) to plus n(i). So the Kramer-Rao bound is computed exactly the same way, except that, you know, the range of computation doesn't let me copy. No, I do it again. So in this pinky, so what I need to calculate is covariance of A, let me call A pinky and B, okay? Now the B pinky is equal to B. A pinky is different from A black, okay? Because one is the intercept on one side, the other is the intercept in the center, okay? Now, so let's continue with the pinky one. So this is equal now, you know, is sigma squared W, and it is H transpose H to the minus 1, which is a copy, okay? Now this H transpose H is this n here, then here is sum of k is going from minus n up to n up of k. Then I have sum of k is going from minus n up n up of k. And then I have a sum of k equal minus n up n up of k squared. If you compare this with the previous one, the only point where it changes is only in the extreme of the sum. Before it was k going from 0 to n, and now it's going from minus n up to n up. Because, you know, the points are symmetrically evaluated. But, you know, this is 0. Because, I mean, I'm summing, so I have k, so I have 1 minus 1, plus 2 minus 2, plus 3 minus 3. Okay, so that's it. Okay? And, you know, and since the symmetric is 0 as well. And so this one is equal to, let me see if I have it. Okay, this one is n squared minus 1 divided by 12. So I need to compute the inverse for that. So the inverse says the following, that the variance of A, the intercept, okay, the peak intercept, is larger or equal than, you know, is sigma squared W divided by n. And the variance of B is larger or equal than 12 sigma squared W divided by n squared minus 1. Now, what do I learn from here? First of all, parameters are not coupled. So that one is 0. Okay? In the matrix of the covariance, the Fisher information matrix is diagonal and the inverse is diagonal. So the parameters are not coupled. Second good news, the variance for that is the same as before. Good. So I'm not losing. So the quality of estimating the slope is not dependent on where I put the axis. Okay, that's good news. But you know, I expected that. Because I mean, I'm simply changing where I'm counting the zeros. And what about this one? This one, you know, before there was a 4 here. 4. Go there. It's 4. Now is 1. So that means that it's a smaller. So the variance is smaller than before. It is 1/4 smaller. This is all doing theoretical analysis. I'm not doing the estimator. By the way, in this example, the estimator is trivial because it's linear. But you see, I can do it in a more general way for any estimator. So all of these reasoning, it can be done without touching the estimator at all. So what I conclude from this exercise is the following. If I need to make a linear regression and my goal is to estimate B, it is more convenient to count the samples from the center, because in case I need the intercept A, in that case is, you know, the variance is smaller. Second conclusion, having the parameter decoupled, okay, so not coupled because, you know, it's 0, means that, I mean, it's like holding the stick, okay? So, you know, my dynamical movement is made by translation and rotation. This reference system is a privileged one for that translation and rotation, so for the dynamic of rigid bodies. Now, in this way, we are deriving a similar conclusion, which means in case I need to handle a linear regression and I want to keep a separate, which means decouple, the estimation of the parameter of the intercept from the estimation of the parameter of the slope, if I do by centering the axis at the center of all the samples, I get a better variance, and the parameter are decoupled. Everything by not doing the estimator. Now, so concluding, you know, if I make this analysis before, I can theoretically get some results of what I need to do, which is guided in some setting the estimator. So when I need to derive the estimator, when I need to optimize the estimator and so on. And I think we are done because they kicked us out. Okay, so I made a little bit opposing one with another, only for the sake of making a little bit of exercise on Friday, okay, on this one, so that, you know, next week you have also time to exercise on that. When I come back from China, we do Friday, we recover all the pieces that we left behind, which is we do the least square, and we do the cameral bound, which is what is missing now, what we're missing today.